I'm Dr. Nathan Schweitzner, and in this video we're going to talk about the really important underlying concepts for determination of average grain size using ASTM E112 as it relates to the quantitative metallographic microstructure assessment for line pipe steels. ASTM E112 is all about how to estimate the grain size of your metal or alloy, but the standard can actually be applied to anything that exhibits grains. It could be applied to crystals or cell size or even bubbles. ASTM E112 is intended for single phase microstructures like this schematic of mild steel, but if there are only minor amounts of second phase, it can still be easily applied to determine the grain size. However, if there are large amounts of second phase, as in this micrograph of duplex steel with light phases and dark phase regions, then ASTM E562 should be used first to estimate the amounts of the different phases, and then ASTM E112 can be carefully applied to estimate the grain size. ASTM E112 is intended for grain size estimation where all of the grains are about the same size, not bimodal, like in this image where there are big grains and then little grains, or multimodal. The assumed distributions are approximately log normal, and if there are other types of distributions, then other standards should be used. It's important to understand that ASTM E112 is for analyzing two-dimensional cuts of three-dimensional microstructures. So if we imagine even a perfect three-dimensional microstructure where all of the grains are the exact same size, if you cross-section this material, you'll see a variety of large cross-sections and small cross-sections. So an important concept as we move into grain size analysis is that the variety and the average size of the grains that we look at in the 2D planar cut is not the same as the three-dimensional grain diameter. Similarly, we need to keep in mind that the two-dimensional cut of the three-dimensional microstructure might not be telling us the whole story. So a two-dimensional cut might be representative of three dimensions, all three dimensions, for roughly equiax grains. But for cases where we have rod-shaped or planar morphologies or odd shapes, the 2D microstructure might look different. The cross-section for rod shape might actually depend on the orientation of the rod shapes, and the cross-section similarly of pancake or plate shapes might depend on the orientation of those shapes. So morphology, we need to keep in mind, is a three-dimensional concept. And two important morphologies for our low carbon steels for our line pipe are equiaxed and elongated. And those have been simplified in these simulations here where you can see the equiaxed morphology roughly would appear the same in a cross-section of any orientation, whereas the elongated morphology would provide different appearances of the grains in different cross-sections. ASTM E112 suggests that elongated grains should be evaluated on multiple planes to estimate the mean grain size. ASTM E112 provides manual procedures for counting or comparing grain sizes. For automated procedures, there's another ASTM standard, ASTM 1382. The standard defines a grain boundary as a narrow transition region in a multicrystalline material from one orientation to the next. That region separates one adjacent grain from another. So here we see some rows of atoms forming the crystal structure and how they are different in alignment from the rows of atoms from another grain, and that boundary between them is the grain boundary. So on a 2D plane, through a 3D polycrystalline material, the grain edges between adjacent grains surrounding a single grain make up the outline of the 2D grains that are observed in the light microscope, and that's what we're measuring. Now let's take a moment to talk about this very important concept of magnification. In each of our procedures, we're always going to calculate the actual magnification, and we're not going to rely on values of reported magnification. For case in point, I have the same micrograph here, reportedly recorded at 500x, but even though they're the same and they were reportedly recorded at 500x, are these the same magnification? The answer obviously is no. When we look at the scale bar here, the scale bars for the two images are two different sizes. So these are not at the same magnification. To know what the actual magnification is, you would have to take a ruler and measure the scale bar on your own computer screen, because from my computer screen to your computer screen, the magnification changes again, and then calculate the magnification based on your measurement on your screen of the scale bar for each of these images. So it does make a difference whether we view the image in the microstructure, on the computer screen, or on a printout or on a projection. Every time you change media, you change the magnification. And since on a computer, it's so easy to cut and paste and crop and resize, we always have to be careful about what we're doing to the magnification of the image during and before our analysis. ASTM E112 provides detailed procedures for three different methods of determining average grain size. Firstly, the planimetric method, where we count the number of grains in an area, and those grains are counted differently depending on whether they lie on the perimeter of the area or wholly contained within the area, and then that number is normalized by the actual size, the actual area. Secondly, the linear intercept method, where we count the number of intersections along lines of known length, and we normalize over the total line length. And finally, the comparison method, where templates of known grain size are compared to our image, and we find the closest match.